Welcome to Hartman Math. Today we're going to look at linear programming. For that we've got a warm-up from earlier in Chapter 7. Go ahead and pause the video here until you've worked through problems 1 and 2. Number 1, the partial fraction decomposition. We want to factor our denominator, and we're going to get repeated linear factors, x plus 2 squared. So we're going to need to break this up into a over x plus 2, the singular factor, and then b over x plus 2 squared, the repeated factor. So then when we add these together, this is our LCD, so we really don't need to mess with this one. This one's missing an x plus 2, multiplied top and bottom by x plus 2. So our numerator is a times the quantity x plus 2 plus b, and that's going to be equivalent to 5x plus 12. So as far as our x's go, we're going to have one equation for x's. A, nothing, equals 5. And then for our constant, 2a plus b is positive 12. So that's our system. Clearly we know a. If we just do direct substitution, 10 plus b equals 12. B is going to be 2. So here's our partial fraction decomposition. Number 2, we're going to want to solve this by the elimination method. So right away, probably x would be pretty easy to do. We've got a coefficient of 1 and negative 1. Both of those are good. If we just add these top two equations, we're going to get, and eliminate those, we're going to get y minus 3z is equal to negative 8. And I think I might choose these two, although you might have done something different, which is fine. So if I multiply this one by positive 2 and add to this one, we can get those to go away. So 6y plus 4y is 10y. 4z minus 3z is plus 1z. And then negative 10 and negative 8 make negative 18. At that point, we could really choose y or z to figure out, see if we can eliminate. But I do kind of like the fact that the z's are opposite signs. So if we multiply this one by 3 and add, we're going to get this. The z's will be eliminated. We get 31y is equal to negative 62. Therefore, y is equal to negative 2. Go back into one of these. Since we're trying to find z, I might use this one here. Negative 20 plus z is equal to negative 18. Actually, it looks like I used the other one. Solve that, you get z equals 2. And then one of these to find the x. Maybe that one. X. And then negative 2 times negative 2 is the positive 4. 2 times negative 5 is the negative 10. And we solve that one for x. We get 3. So our order triple, x comma y comma z, 3 comma negative 2 comma 2, definitely need the parentheses. All right, lesson 7.6, linear programming, one of my favorites in this book. You can see how higher level mathematics can be applied to real world situation kind of things. We'll kind of do it at a low level here, but it can be ramped up if we introduce more constraints. But what we want to take a look at is we're going to be given some constraints, and that's going to create a region of feasible solutions. So we kind of think back to 7.5 when we graphed some systems of inequalities. We had this shaded region that represented all of our solutions. Well, we have that here, and we're going to be concerned with the vertices, all the corners. So we want to, 1, sketch it. 2, make sure we can find all of the vertices. We're going to list those in a table. And then we're going to evaluate the objective function, whatever we're trying to either maximize or minimize, and evaluate that at each of the vertices. And then we're going to see what's best and what's worst. So example number 1, here's our objective function. Z is equal to 2 times x plus 8 times y. Here are our constraints. We've got x is greater than or equal to 0, y is greater than or equal to 0, and 2x plus y less than or equal to 4. So x greater than or equal to 0, we're talking about vertical, shade right. Y greater than or equal to 0, horizontal, shade up. So now we're only talking about quadrant number 1. And we could do this one by finding intercepts. The x-intercept is 2. The y-intercept is 4. So we've got that. And then we're going to shade. If we pick a test point, 0 and 0, it makes it true. So we're going to shade the side of 0, 0. And there is the feasible solutions. So we're talking about vertices of 0, 0, 2, 0, and 0, 4. So we're going to list those in a table. So points, and then on the other side we're going to have our z, our objective function. So our vertices, 0, 0. If we plug in 0 for both, we're going to get 0. And then we've got 2, 0. So 2 times 2 plus 8 times 0 is 4. And then we've got 0, 4. So 2 times 0 plus 8 times 4 makes 32. So the worst, the minimum is 0, and it occurs at. The maximum is 32, and it occurs at. Example number 2, something a little, something similar. One additional constraint here, so z is equal to 2x plus 7y. Our familiar, x is greater than or equal to 0, y is greater than or equal to 0, and then a couple more constraints there. You might notice that I've changed the scale here to go by 2's both ways. It is possible just to change the scale one way. We are changing it 2 in both directions. All right, so we know about these. This basically just means quadrant 1. So now we're looking at this one. So by intercepts, x-intercept is 10, y-intercept is 4, 10, 4. And then we're going to be shading inside on that one. This one, we've got x-intercept is 8, y-intercept is 2. And if we plug in zeros, we're going to get zeros greater than or equal to 8, so we're not going to shade that side. We're going to shade the other side, which means we're shading above. So below this one, above that one, so we're talking about shading in the middle. So there's all of our feasible solutions. So we're going to use that. We're going to create a table for all of the vertices. 8, 0. 2 times 8 plus 7 times 0, 16. 10, 0, 20. Over here, I just kind of like to go in a circle. We got 0, 4. 2 times 0 plus 7 times 4, 28. And then 0, 2. 14. So if that's our function, the worst, the lowest, minimum is 14, occurs at. Maximum is 28 and occurs at. So obviously if we look at our objective function, the 7 has quite an influence. Now on to some application stuff. Example number 5, optimal profit. A manufacturer wants to maximize the profit of 2 products. We got product 1, which yields a profit of $1.50 per unit produced, and product 2, which profits $2 per unit produced. How much of each type should be made in order to maximize profit? We probably can't just make as billions and billions. Because here are our constraints. This is what our limitations are for the manufacturing process. The combined level of production cannot exceed 1,200 units. So whether it's materials or labor, we're just limited by what we have here. So 1,200 units per month. Demand for P is no more than half the demand for P1. And the production level of P1 is less than or equal to 600 units, plus 3 times the production level of product 2. So we're going to take each of those constraints, and we're going to have to write a system of linear inequalities. All right, so we're going to need to define our variables. Again, since we're going to be using a graph, we're going to want x and a y-axis. We're going to want to use x and y. So x is going to be the number of P1 that we produce, and y is going to be the number of P2 that we produce. All right, combined production level should not exceed 1,200. So production level, that would be the x plus the y, has to be less than or equal to the 1,200. Let's go back for a second, look at the other one. Demand for P2 is no more than half the demand for P1. Demand for P2 is no more than, which means less than or equal to, half the demand for P1. And production level of P1 is less than or equal to 600 plus 3 times the production level of 2, which was y. That would be our inequality there. Okay. Now what we're also have not listed, but we are implying, since you cannot produce negative amounts of product 1 or 2, we're also going to assume that x is greater than or equal to 0 and y is greater than or equal to 0. So everything that we're going to graph has to be in quadrant 1. So we're going to do it such that each of these is worth 200 units. So we're going by 200s on our scale. So by intercepts, x-intercept 1,200, y-intercept 1,200, there to there. And that's going to be shade inside. This one's pretty reasonable. Notice that we did have a consistent scale. So we're talking about y equals mx plus b. The y-intercept is 0. The slope is 1/2, up 1, right 2. And that's really 200 and 400. But that still has a ratio of 1/2. So there's that one. And that one is y is less than, so that's going to be shade below. And then this one's a little bit tricky because this is not a form that we're really used to. So maybe we could either solve for y or put it into standard form. If we solve for y, we'd get y is greater than or equal to 1/3 x minus 200. So y-intercept, slope of up 1, right 3, going there. And it's greater than, so we're going to shade above. So remember, we're also, everything's in quadrant 1, so here's our optimal region. So some of these are pretty obvious, 0, 0, 600, 0. This one's not as obvious. That one's pretty clear, and it's the better you do at the graphing, the easier it is for us to be able to find these. That one's 800, 400. But this one's a bit of a challenge because we're kind of guessing where that might be. So we're going to have to go back to our system. First of all, we have to identify which of these are intersecting right there. So we've got the first one. That's that one. And then this one, the one that we just came up with. And whether we go with either one of these versions is fine. So I might say go right there. So that's our system. Those two inequalities are intersecting right there. So if we took those, pretend they're equals for a moment, and solve the system of just those two, we're going to come up with the coordinates there. So we could do direct substitution, basically saying x is equal to 3y plus 600. So 3y plus 600 plus y is equal to 1,200. So subtract 600 both sides. 4y is equal to 600. The y is going to be 150. And then if we plug that in here, that means x has to be 1050. So that's how we're going to get those points of intersection, is figure out which lines are intersecting there, choose those to solve that system. All right, let's turn these into tables for our vertices. All right, so we did have 0, 0. And our function value is profit. So if we make nothing, we profit nothing. Probably not the optimal situation. And then we've got 600, 0, so 1.5 times 600 makes 900. We could do the 1050, 150. So 1.5 times the 1050 plus 2 times the 150, we would get 1875. And then we lastly have 800, 400. 1.5 times 800 plus 2 times 400, we would get 2,000. So in this case, we're not really concerned about maximum and minimum. We want to, as a business, maximize the profit. So we're going after this. That's how we would do it. We would make 800 of product 1 and 400 of product 2. And if the question, hey, what's the maximum profit? We would say it's 2,000. So it really just depends how the problem is being phrased. What should we do? What do you get? We'll do one more like this. So this will be example 5 plus. Optimal profit. Furniture manufacturer makes 2 kinds of coffee tables. Circular table requires 3 hours of skilled labor and 6 hours of unskilled. Produces a profit of $50 for each of the circular tables that are produced. Rectangular tables require 2 hours of each type of labor, 2 of skilled and 2 of unskilled. And we profit $30 from those. If 90 hours of skilled and labor is available and 120 hours of unskilled are available for the week, how many of each type of table should be made for the week in order to maximize the profit? So we're going to basically say that you are the consultant that the business has hired, and you're supposed to tell them what they should do. All right, we're going to start with our let statement. There are 2 different types of tables, the circular and the rectangular, and we're going to use X and Y. So X is the number of circular, Y is the number of rectangular tables that we're going to make. Okay? We've got to figure out what is our function that we want to maximize. We're going to want to try to maximize profit. What is profit? We're going to get 50 for each of these and 30 for each of these. So there's our profit function, 50x plus 30y. Now our constraints are based off of our labor situation. So let's go back and look at that. So we're going to have a constraint for skilled labor. So kind of think about that, maybe pause here. Can you come up with the constraint for skilled labor and the constraint for unskilled labor? All right, so what we should come up with for skilled is, since circular tables take 3 hours, 3x plus 2y is less than or equal to the 90 hours of skilled that we have. And for unskilled, 3x plus 2y is less than or equal to the 120. So we got a skilled constraint and an unskilled constraint. And once again, we're not making negative amounts of tables, so we're also talking about x is greater than or equal to 0, y is greater than or equal to 0. All right, our scale, we're going to go by tens. And we're going to find intercepts. We've got 30, 0, 0, 45. 30, 0, 0, 45. And then we've got 20, 0, and 0, 60. So it's pretty clear, if we've done a very accurate job, that we are intersecting here at 10, 30. So our vertices 0, 0, 20, 0, 10, 30, 0, 45. Again, if we make nothing, we profit nothing. 20, 0, we can make, if we only make the circular, profit 1,000. If we make 10 and 30, profit 1,400. What about 0, 45? Very close, 1,350. But here's where we're going to go. If we make 10 circular and 30 rectangular, we will profit 1,400. So that's what we should tell the business to do. That's it for today. I'll see you next time.